It concerns these buy problems, like restriction to buy directed systems, or maybe question about buy reachability, which are very closely related, for a different extension of VAS. Not push-down VAS, but this time my favorite models of data VAS. What is data VAS? Who knows? Whoever has ever seen data VAS. Okay, so in one sentence, in the knowledge of Petri-nets, what changes? What's the extension? In a classical plain Petri-net, there's a transition, right? With input and output places. And what you expect to specify a transition, like number of tokens. Like 2 tokens here and 1 token there, 1 token here, right?
Okay, change to black color.
Green one. Your favorite color. Green. The black one. With data, what changes? Tokens are no more anonymous. They are like colorful, or they carry data. Each token carries a datum. So to specify a transition, I need more information. Not like how many tokens, but how the data are related. Easy. I just replace numbers by variables like x, y, z, and w, right? 4 tokens involved, and now I specify equalities, say, between data, right? This is an example specification, so I care that these 2 guys have the same datum, different than this guy, and what about this output guy? I don't care, and equal or not to any of the input ones, right? Some simple example. So this is the model, this is my favorite model of computation, data VAS.
Universe or finite universe? Infinite universe or finite universe?
Excuse me?
Like
The data comes from an infinite set. Good question. And in this example, I just used equality. So this is the simplest case. But you can imagine richer domains when you, for instance, may specify an order between data in case of ordered data universe. Good. What problems for this model? So the problems you've seen in the morning, I will do a list or short list of problems. So there is reachability, question, source to target, graph. There is this bidirected case, so there is reachability in bidirected subclass. When the question looks like for 2 configurations, the arrows are symmetric. In the middle, you can find yet another problem. I would call it bi-reach. Again, for 2 configurations, I'm asking about the mutual reachability, or bi-reachability, maybe by 2 different paths. This is a restricted subclass. This is non-restricted general class, right? As in. And there is coverability around, which I did not mention. And it happens that this is the order of difficulty between the problems. For whatever models we consider, like plain VAS, push-down VAS, data VAS, it always go like this. Okay? Now for data VAS, let's look at the situation. Yeah, a small table. There will be equality data, like in this example, or maybe a richer structure, like, say, densely ordered data, rational numbers. Okay. What do we know? So, coverability not shown here is decidable in both cases, okay, by WQ. Now, concerning from the simplest, by reach in the Georg's terminology. So this is the problem of this morning. Up to very recently, nothing was known, like actually on this question, until very recently, as a kind of corollary of some more general results, using ideals of polynomials over infinite set of variables, very quickly speaking, we can show decidability here. Okay. Fine. Concerning the hardness, the reachability, it's well known that this is undecidable. Okay. And now the middle part is maybe the most interesting. So, by a very recent finding, we know now, it's a result with Łukasz Kamiński, which is here, we know decidability here. And that's it. What we know, right? So the open problem is what's remaining. So there is like a big open problem, which is probably very hard. Namely, reachability in vast with equality data. We are working recently with Łukasz. We have some progress here. We even, from time to time, we think we have it, but it's not here. Another nice question is this one. Maybe a smaller question. So we ask about bi-reachability, but the data universe is ordered. So okay, you are tempted by two contrary possibilities. None of this works. We tried. So neither our techniques from equality data can be extended to order data. The things break very quickly. Neither the very simple reduction here, very simple undecidability argument, seems to fail miserably when you go to buy the symmetric question, right? This buy question. It seems to break as well. So this is my open question. This is an old question, which is probably hard. This is a very new one, maybe easier. That's it.
Questions?
So if you allow new transition to create fresh colors, do any of can any of the plus remain?
Here the answer is
yes.
known.
But for the pluses?
With order you can kind of simulate freshness. So I guess it doesn't work, the undecidability argument, because it's very similar here and with fresh.
But for the one at the bottom left?
You mean, I mean this one?
No, in the unordered.
This?
No, unordered data. This color.
Yes, so once you have order, you can simulate fresh on equality data. Kind of, yeah. Sufficiently well to have undecidability.
Bottom left.
Yes.
So
this. I mean, you have
fresh.
Unordered data, but you can create fresh.
Fresh.
But you don't have to answer.
I don't know.
Okay.
I don't know.
But how does bidirected work if you can create fresh data?
Oh.
Like, what does it mean to delete the data you introduced?
That's not the subclass, yeah? So
yeah, so how is the subclass defined if you have bidirectedness? Like, I don't see how freshness and bidirectedness, like, how do you define this class even? I mean, a transition which introduces a new data, how do you turn it around? Like, you have to kind of say that you delete now data from everyone in the system, right?
So you forbid using this data. This data is never allowed to be used.
Okay,
and this is the only token with this data, and you forbid
keep the technical part.
Yeah, so no idea.
Okay.
Fresh. I never looked really into this. Yeah.
Yes, I'm wondering, so you mentioned the rational numbers for the set of data. So it's a done set. I mean, it's always possible to find an element between two elements. If you consider some other order, like the natural numbers, you have some undecidability result for the bi-reachability?
Quickly, I don't know. What about like the naturals, right? As domain. With integers.
When you mentioned that for right directive, you have decidability.
With integers, still this undecidability holds, right? But with natural numbers as well, you can still. I can redo this.
Yes, but if you are in the by deal or model, but you cannot define
So this will work still, because that's fine, because the idea of proving reachability here is, or deciding reachability here is by polynomial ideal membership. And then we have like a generic result for different kinds of variable domains, right? Because variables come from an infinite set now. And like every well-ordered domain is fine. Like if you get this ability of polynomial ideal membership. So like natural numbers are fine. Integers, I'm not sure about integers, but it should be also fine, I guess. But it's like a for a range of variable domains you have it.
Okay, thanks.
Okay.
I propose to move on.
Thank you. Yeah.
So I found the list. David's on the list.
Okay.
Okay, so who knows what a weighted automaton is? And now invert your hands. Okay, so some people don't know what a weighted automaton is. So, a weighted automaton is an automaton with numbers on the transitions. Okay, so here is an example of a weighted automaton, which creates a function from a word, finite words, to numbers. So in this case, it will go to the integers. And how do we do this? So, well, it depends what semi-ring you're in, but over the rational semi-ring, you take products along any run. So we can look at a run. Let's, for example, consider the run on a word AAA. So one such run here would be to go A. I didn't mark any states as final, but maybe I should have done. So let's mark that as final. So that run would have weight 2 times 2 times 2. So it would have weight 8. Okay? And there are many runs of weight 8, right? So I could have gone 2, 2, 2, or I could have gone 2, 2, 2. So there were 3 runs of that. So what do? When I have multiple runs, I add them up. Okay? So the weight of this would be 8 plus 8 plus 8 plus whatever you can do in here, but it doesn't reach any accepting runs. Okay? Is it clear to everyone what we do? So we take products along the run, and then we sum up all the runs. Okay, so this is what a weighted automaton is, and the problem I want to know is, or the problem I'm interested in is, given a weighted automaton, let's say A, does there exist a weighted automaton B that is unambiguous and A is equal to B, which means for every word it produces the same output. Okay, so this is the unambiguization problem, or whatever you want to call that problem. It's known to be decidable due to at least Daniel Smirnik and Jason Bell, so that's not in question. The question is, what about lower bounds? Okay, so the decidability result has no complexity, essentially. If you can make a complexity from it, it's still going to be a very high complexity from that algorithm. But I don't know any result other than NL hardness. So I can't imagine it is NL hardness. I would aim for something like NP hardness first. P-space might be a reasonable guess for the final problem, but basically any technique to improve the lower bounds is what I'm after. As a side note, the problem, So this was for the rational semi-ring. I'm also interested in exactly the same problem for the min plus semi-ring. So min and plus, so what you do there, along the run you add up, and then once you have a set of runs, all that have a value, you want to take the minimum run. So the weight of your word is the weight of the minimum run. And there, the unambiguization problem is going to be decidable if A is polynomially ambiguous. Then you can decide if there exists B that is unambiguous. Okay, but if A is not known to be, if A is not guaranteed to be polynomially ambiguous, it's a big open problem. But still, as far as I'm aware, there's no lower bounds for this problem in this setting. So for the lower bounds, I would be happy if you don't impose the polynomially ambiguous restriction. Just for a general given weighted automaton, can you produce any non-trivial lower bound for does there exist an equivalent unambiguous weighted automaton? Any questions? Yes?
So what does unambiguous mean? Just one run per word, or?
Ah, yeah, that's a good. Could have stopped me earlier. Right, so an automaton is unambiguous if exactly that. There is exactly one run per word. So it's not quite deterministic. There could be multiple runs existing, but only one of them at the end of the word will be accepting.
At most one.
At most one. There could be 0 runs. Yeah? And it's completely about the underlying graph, right? You just remove, well, and the labels, but nothing about the weights makes it, the weights don't affect the ambiguity of the given representation. Of course, it will change whether it is unambiguizable. And just to make it clear, if a weighted automaton is unambiguous, then you will only have one run, so you will only take products, right? So the sum will never be used. So that's the important part for a weighted automaton. So basically, is there a representation of the same function that never uses the sum, only uses product? Or for this, never uses min, only uses sum.
For min plus, don't we get piece-based hardness from NFA universal?
I don't know.
My question?
So for min plus, whether we get piece-based hardness from NFA universal?
How?
I think the reduction to NFA universal will give you something unambiguous if it's, or unambiguizable if it's non-universal. And then it doesn't work for the field, but for min plus I think it might work.
Okay, good.
I think I'm not sure.
Well, you can tell me later. And maybe this is wrong, but definitely there's no lower bounds for the plus times.
There is, I think, when we were in February, we know it's not a lower bound, but we know that the equivalent automaton B could be of exponential size, right? Or I'm wrong.
But I think it was for the deterministic.
Oh shit.
It could be that there's a small
Yeah, you're right. So,
Yeah, you can also ask the whole same question for does there exist B that's deterministic? And lower bounds for that are also interesting.
more questions?
Yes, yes, I have a question. What is the upper bound? Because you mentioned it's decidable.
For decidable, what's the upper bound?
Yes.
I don't think there's any known upper bound. Is that right?
on the runtime.
No, there's no upper bound on the runtime. If it's polynomially ambiguous, then there is p space upper bound, but it's not clear this is tight by any means. Although a lower bound making it tight would be nice.
Okay. So let's thank David. And David forgot to say, but if you got interested but you're not sure what's weighted automata, he's very happy to teach you.
Sure.
So,
Next slide.
Slides.
Yeah, that's fine. I can find out. Thank you for the lecture.
slides.
It's a problem.
Hmm?
The problem right there.
So I spent 10 minutes making the slides and I'm very proud of it. I decided to keep it titled because it's so concise. Right, so reachability in VAS, VAS without S, so VAS not VAS. We all know what that is. Start with some configuration, let's say 0, 0, and you want to hit a target X, Y. And I want to talk about something called box reachability. So the idea is this. You're given your target X, Y. Let's draw a box defined by X, Y, and ask whether there is a run that reaches this X, Y without going outside of this box.
Yeah!
So there is a run. And the question is very simple, it's the open question. What does the box reachability set look like? So what is the set of configurations that you can reach using runs that do not go outside the bounds given by the configuration? So this is the open question, but I can say some more things about it. So first of all, if you're given the configuration XY, it's trivial to decide if there is a run that reaches it, because everything that was bounded, you just have to try and find a solution. That's not interesting. But if you look at the set of box reachability, it could be very different from the reachability set, or somewhat different. Now, before I'll read this, this approach is very different to the standard approaches to reachability that use linear path schemes. Because in linear path schemes, what you essentially do is you pump cycles. So the simplest runs might take you very far outside the box and then come back very far. And you definitely go outside the box when you use it. And this has very different requirements to it, which I like. Now, if you look at an example, consider a VAS that has two vectors, 1, 1, and 1, minus 1. So the target 2, 0 is reachable, because you can just do 1, 1 plus 1, minus 1. But it's not box reachable, because if you want to reach 2, 0, then the box defined is just on the x-axis, and you just can't reach it. So these sets are different. Definitely the box reachability is contained in reachability, but not vice versa. So the question becomes slightly more interesting. What is that set? So as another example, take this VAS, for example. You have three vectors. You have 10, 10, which is a big green arrow, and you have the vectors minus 1, 2, and 2, minus 1, the other two green arrows. And let's look, for example, at the configuration 11, 11. Is it box reachable? So you can construct the vector 1, 1 that you want to add to 10, 10 using the vectors minus 1, 2 plus 2, minus 1. But if you construct it this way, then these arrows go outside of the box, of their own box. So you actually can't reach 11, 11 within its box, because you'll take 10, 10, that's your only option to start with, and then you're stuck. So that's fascinating. What about, wait, what happened? Yeah. What about 21, 21? Is that box reachable? It looks very much like 11, 11, but this one is box reachable, because now what you do is you start with 10, 10, and now you've gained some wriggle room, because you still have your target far away, you're still within the box, but you can start playing with the vectors. Now you can add minus 1, 2, and 2, minus 1, and you have 11, 11, and now you take 10, 10 again, and you reach 21, 21. But this is very much not like linear path schemes, right? This requires you to combine vectors in a very specific order. So this is an interesting thing. And this observation, mainly the thing that you need to take 10, 10 to begin with in order to have something to play with, led us to the thought that maybe if you remove some big L shape, which is a fairly standard technique in VAS reachability, outside of this L shape, which is kind of one-dimensional, the remaining infinite plane coincides in its reachability with box reachability. So anything in the white area is reachable if and only if it's box reachable. That's the conjecture. I don't know if it's true. Maybe it's not, maybe it's easy to prove that it is, maybe it's easy to prove that it isn't.
It's not like this that you need to kind of remove 2L, so this one
also
and
the
this
O.
one.
Yeah, so another conjecture that I didn't have time to add is that maybe it's not a, so it doesn't clearly make sense what it means to remove an O shape, because you're not given the target configuration. We're asking what is the shape of the entire reachability set of this. So you can't actually remove a fixed band, but maybe reasoning about it requires you to remove a fixed band around the target while you're reasoning about it. I don't know, but this is certainly something we're looking at. So the open question is just what is the reachability set, but some variants of it that are interesting is max box and sum box. So I ask what happens if you take a box that is x on the x-axis and y on the y-axis. But you can also take a box that is the maximum of the coordinates, or the sum of the coordinates, or anything else you feel like. So what is the motivation behind this whole thing? in a lot of VAS problems that we reason about, the actual VASs we end up with have a very similar shape, where they start by charging some resource, number of processes or some, I don't know, consumable. So you charge it up, and then the remaining of the configuration doesn't go beyond that bound. You have a fixed number of things to play with, but you first charge them. And this is what this does. You need to charge some element, but then you stay within its box for the rest of the computation. The question is, what do these VASs look like? And the more I'm stuck with this problem, the more I like it, because it also has some flavor of symmetry with standard VAS. In standard VAS, we limit the configurations not to go below 0, but why do we not limit them to go beyond some upper bounds? So if you just fix an upper bound, the question becomes trivial. If you don't fix an upper bound, you get this. So all this general existential boundedness problems I find interesting. That's it.
Thanks. Questions?
Yes, I have a question. So you are looking at this problem in dimension 2.
Yes, dimension 2, sorry.
Yes, because otherwise you can encode with extra dimension, you can encode the box sketchability also.
Yeah, so once in dimension 3 and so in VAS without S, it's in dimension 5, you still get this non-semilinear behavior, and depends on the example if you take it in reverse. So yeah, it gets ugly in high dimensions. We're starting with 2 dimensions.
It's like, yes, because it's like looking at a reachability problem with some constraints on the number of that we can obtain along the way. And rather than looking at this number with respect to the final configuration, it can be with respect to some other variables, some fixed parameters.
They can't be very fixed. They need to be given as input. You need to play with them a bit, but yes. Some function of the target.
Yeah, it's flex. Looking at reachability question parameterized by some numbers, no?
Yes, parameterized by something that should depend on the configuration, ideally. Or parameterized by something, I guess. It makes equal sense. But it might be harder if you just allow the parameter to be weird.
Any more questions? All right, thanks.
Może po kolei.
Po kolei. Michał, do you want to say something?
Okay, actually I have 2 problems.
Dajcie to,
Can get one.
dajcie trochę, żeby tego, żeby trochę do tyłu, żeby na to może być.
Should I actually give both of them, or the one that is actually serious? That's one, and second is just durability.
Definitely a serious one, but both of us, of course.
Yeah, okay, so I will give 2 problems. One more serious, and second is less serious, but actually both of them are valid research problems. Okay, so the first problem is actually a little bit connected to this discussion about VASs being parameterized. So when you think about an instance of the VAS problem, what do you have? You have let's call this a transition system D, yeah, which consists of the vectors and the space, the transitions, and so this consists of transitions of the form from some state P, go to some state Q, and add some vector, I don't know, U. Yeah, so a finite set of this kind of rules. Yeah, where this U belongs to Z power D.
Excuse me, can you try to draw thicker lines? It's really not visible.
I see, okay. Yeah. Is this better?
Yeah, much better.
Good.
What is on the arrow?
Yeah, over the arrow,
Which arrow?
there is a vector U which belongs to Z power D. Yeah? And these 2 guys, P and Q, belong to some state set Q. Yeah, so this is a finite set of rules like that. And moreover, in the, say, reachability or coverability problem, you also have two vectors, S and T, both belonging to n power d, and you ask whether, for example, T is reachable from S using these transitions, or, and, oh, okay, you have probably also a Q0 and Q final. These are the beginning state and the final state. Then you ask about the reachability or coverability or this kind of questions. So naturally, if you work in the area of parameterized complexity, it is natural to try to fiddle what can be in this input specification considered small and what can be considered large. And looking at that, at least to me, it is natural to consider the system, the automaton, to be kind of fixed, yeah? And this is the actual input, and these numbers can be large. Okay, so this is the motivation, but the actual question is the following. Is, okay, maybe a conjecture simply. Yeah. If from state S, maybe even, yeah, if from S, comma, Q0, I can reach T, Q final, yeah, using my transition system D, then actually I can reach, then there is a path, a reachability path of length bounded by, and now some function of the system times, let me be bold and say, linear in the counters that I get at the beginning. Yes?
I think this conjecture has been made before by Michael Hack in the 70s.
In the 70s?
Yeah. I know this as Hack's conjecture.
Okay.
Yeah.
So, yeah, at least from the point of view of parameter complexity, this would be a very natural question. Like, this would be, in terms of that, it would be about fifth parameter tractability of the vast parameters by the size of the transition system alone. Yeah. For this purpose, you could also put here any constant, so order of 1. Yeah. So this is for reachability, but as far as I understand, even for coverability. This is unknown. Does it make sense? Yeah? So if I can cover the target T, yeah, from S, then I can cover it also with a bound that is polynomial in the sizes of the counters at the beginning times some function of the description of the system. Yeah, so in this sense, the vectors that I can add and remove are constant, but the sources and the targets are actually can be large. And maybe for coverability, this question is actually could be simpler, significantly simpler than for reachability. Yeah.
One problem will be.
Oh. So if you replace the sort by a difference, I mean, rather than looking at S infinity plus T infinity, you look at S minus T infinity. Do we have some counter examples?
I don't know.
Because, I mean, if the system is, if you look at a bidirected bus, we know it is the case.
Yeah. I don't think that we have a counterexample for the difference. This could also be true if the numbers are large but they are close to each other, that you can actually have a run that is within the area of the source and the target. Yeah. And this would actually probably could make sense, right? Because if the numbers are large, you are probably in this area where actually you don't care about negativity. Yes?
So maybe as motivation, so there is a very obscure, but nevertheless very old open problem in the theory of regulated rewriting, or something called matrix grammars. And if you could prove this conjecture, if you could disprove the conjecture bad enough, then you would solve that problem. So if you find a fixed mass with a reachability problem that's harder than linear space, so this would give you NL, a primary fixed mass. And if you could do the opposite, then you would disprove. You could solve this open problem. So it's connected to that open problem. That's very obscure. But if you need motivation,
well, I think I don't need motivation. I think it's very natural for a question. Yes.
Do you know anything about dimension 1 and 2?
That's actually a good question to the people who work on dimension 1 and 2, but I think that for dimension 2 there is a very good understanding of the VASs, and I think for dimension 2 it's followed. I think
that for VAS with semilinear reachability relation, that's very possible. This is actually normal, right? So that's right, Jerome?
Yeah, yes, I have a technology.
Yeah. So then the real challenge is to prove it for non-semilinear reachability relations, right?
Okay, let's thank Michał. I forgot to say that if you don't want to be recorded, you can tell us, or if you want to be. Okay, we have time for one more person. Roland, do you want to come?
Okay.
Okay, maybe this is a stupid idea. Can you bring the other board?
The other board? Okay.
Would be better to set that with.
Am I in the camera?
Right. Yeah, but rotate the board to board and base toward.
Parallel. Okay.
Oh.
No? Yeah. Okay. So the problem I want to present is about definition for VASs that's like also very old already. It's called weakly computing functions. A weakly computable function. So what's a weakly computable function? So first of all, I guess the obvious definition you might write down at first if you think about a VAS is, okay, you're given a VAS. You're given a VAS with some set of actions A, z to the d. And well, you can also allow states, I guess. And then you're given an initial and a final state. And now I guess what you now you designate one of these, one of the counters. Say the first counter you designate as the input counter. So first counter is the input counter. And you designate some counter as output counter. Say the second one is the output counter or something. And then what you could wonder about is, okay, so given some tuple x, and then in the rest I want to start with zeros. So I start with some value in my input counter, and of course I start in my initial state. I start with 0 in the output counter and 0 in the other counters. And then what I kind of want to characterize is the set of y's, such that there is some vector w, some garbage that will be in the last counters, and there is some garbage that will be in the first counter, such that this q0 can go to the final state, go to this garbage in the first counter, go to the value y that we are interested in the second counter, and go to the garbage in the last counter, and the auxiliary counters. And what's the idea? So you use the auxiliary counters to compute some function that goes from the x's and compute some kind of y. And okay, so in the simplest case, a function that of course you could compute is something like multiplying by 2, because what VAS is just doing is, well, it doesn't even need many states. You just say, hey, I decrease my first counter and I add 2 in the second counter. You don't need any auxiliary stuffs. And then what you would probably say is you have computed the function 2x. And how would you formally define that you have computed this function? Well, how do we formally define that you have computed this function? Well, if we now look at the set of y's such that this condition was fulfilled, right? So the set of y's such that there exists a w vector and an x vector such that the thing I told you about. And we look at this parameterized in x. So this is some set that depends on x. Then this set will be exactly 0. Well, I guess it only includes even numbers. So it will be some set contained in 0, 1 to 2x. And in this sense, you compute the function x goes to 2x because you fulfill 2 conditions. So if you start with a given value of x, you end at most with the value 2x, but you could possibly also end up with smaller numbers. So we explicitly allow this for VAS. And then we call this notion of computing, we call this weakly computing a function. And then, well, VASs can actually compute way more than just linear functions. So they can also compute something like exponentiation. And, well, they can also compute tower. And, well, it's actually not hard to see that they can do this, because 2 to the x you can do similar to Hopcroft-Poisson, or in fact Hopcroft-Poisson is an example that computes this function, if you view the correct counter as input and output. And then you can iterate Hopcroft-Poisson, and you can decide as often as long as I still have tokens in some input counter, I can exponentiate, and this way we would compute tower. And then actually you can compute all the fast-growing functions fd, which are of course defined as fd of n equals, you take fd minus 1 composed with and so on, composed with fd minus 1, a total of n times, and apply it to 1. Right? So these are all functions you can compute. But a question that's pretty old is, I guess, which functions are weakly computable, right? So that's like, I guess, a question that at some point should be answered. Which functions can be weakly computed? Okay, so of course this is like very general question. So I'm first going to give you some basic data, what do we know, and then some maybe doable conjecture, some function that if we could answer this question for this function, it would already help us in a major way. So what do we know? So what we know is that, for example, the inverses of the fast-growing functions, so the FD inverse, cannot be computed. Why is this? This is because if we imagine what a function looks like, so the fast-growing functions are like functions that grow steeper and steeper, while their inverses will do the opposite. They will grow weaker and weaker and weaker. And in general, you can only compute functions which become steeper over time. You cannot compute functions which become more flat. So that's one of Leroux's results at some point. You can only compute functions which become more and more steep. And Yeah, on the other hand, what do we know? Well, of course, we know that we can only compute primitive recursive functions. This is because for every fixed dimension, the vast reachability problem is primitive recursive. So you will not be able to compute a function which is not primitive recursive. Yeah, but this is also basically the only thing we know about upper bounds. And so, well, these are the functions we more or less know are in here. And now there's of course a major difference, like which functions are actually possible. And so there's one function which is of this shape, that it's growing, but whether we can actually compute it or not, no idea. And this function is 2 to the square root of x. And so my open problem is this function weakly computable? Why is this interesting? Okay, so if you actually manage to disprove that this is weakly computable, then you find a third condition here, and it's an important one because you have suddenly broken the record of we can only use decidability and only use some weak primitive recursive argument, or some argument about the function has to become steeper and steeper. You have suddenly broken the aspect of those are the only two things we know about these functions. Suddenly you found a completely new argument for why this is not possible. So this would be great. And also, if it's possible, then you have suddenly managed, why have you suddenly managed to do something important? Well, square root of x is not computable via VAS, because again, it would have this shape. So if you somehow manage to actually weakly compute this function via VAS, then once again, we have done an important step and figured out that even if parts of the function that every normal person would agree is probably necessary in order to compute this function are not computable, the whole product still might be. So either way, if you can answer this conjecture, either way it would make great progress on the question which functions are weakly computable. And I think this is an interesting problem to work on.
Any questions? All right, thanks. Wait.
Maybe I have a question. If you, this is the problem for VAS, if you have a stack, do you think we can, because you mentioned one of my paper, but I think it was about...
Well, so this one...
maybe I have two, yes.
Yeah, you have two. You have one that the same also doesn't work for stack, but originally you also had one that this doesn't work for normal VAS.
So if you have a stack...
But also with the stack, like we have even less idea what can be computed with the stack. But I would suggest we restrict ourselves to normal VASs at first. Like, I have the feeling if we ask this for push-down VAS immediately, we're just going to discourage ourselves.
Okay, one more question.
Yeah.
Do you have any idea how to do x square root of x?
And which one?
X times square root of x.
X times square root of x.
Yeah, I mean it should be intuitively easier.
Okay, so if we differentiate this, then we get x times. No, I mean then the first check is it even of this shape, right? So that's the first check I do. That's why I the computer derivative. So you get x over 1 over 2 square root x.
It's super linear, right?
Plus.
It's super linear. So it's fine.
Yeah. Yeah, right, no, wait. This is actually way easier. You just wrote it in a bad way. This is x to the 3 halves. Yeah, that's definitely x to the 3 halves. How would this one work?
Let's make a soft line because we're done. Sorry.
Yeah, probably. X to the 3 halves.
Okay, so